Good morning. Here we are once again. It's the physics video lecture, Physics 2A video lecture 14. And we're starting a new chapter today. So there will be plenty of review of what we've been doing, especially if you ask me for some problems you'd like to have solved. But we're moving on to chapter 5 and the concept, the topic of energy. Energy, work, and power. So I'll go ahead and give that title. Energy, work, power. And I'll begin with the concept of work. So work has a technical definition in physics. It's not just any old thing you do and get paid for. So work is a force times a displacement. And I'll demonstrate that immediately. Force times displacement. So I brought the physics department bowling ball to class. And that represents a weight, which is, as we know, a force. Yeah, so this thing we may have weighted in class before, now it's about 70 newtons, okay? So that, me holding it up as a force, if I hang it from a string, there's a tension. Now, the work aspect comes in if I lift it. So here's 1 meter, so over my head a bit. If I lift this bowling ball a full meter, then I've displaced it, okay? That's what right, I've moved it from one place to another. That's what we decided was the definition of displacement. And that means I've done work, okay? So you never forget this. If you lift something, some weight, you're doing work. Okay. Let's go ahead and fill in a little bit with that definition there. So work is force times displacement. Example is to lift a massive object. And now we can become a little more technical with this. So my symbols here, I'll say work is equal to force times a delta x. Remember that was our displacement called delta x. And the units of work are the Newton times the meter, so newtons times meters, and that gets its own name. I'll use the letter J, the name is joule. So the unit of work, 1 Newton times 1 meter is a joule. Good, send that up there. And in my example, I could lift the ball off the floor up to my head level, that would be 2 meters, but I'll just put some numbers in like this. Example, work is equal to 70 newtons times, say, 1.5 meters. I lifted the bowling ball up to 1.5 meters. Maybe I rested it on a shelf, okay? And then we would have 70 times 1.5 is 105. 105 joules. So good, units of work are joules. Now before I even talk more about work, I do want to bring in the energy concept right away, because we're still on energy, work, and power. Energy is the capacity to do work. Right now we're still just talking about mechanical work, capacity to do work. So that's the definition of energy. So the units of energy are also joules. And apparently I had the capacity to do 105 joules of work when I lifted the bowling ball up that high. Good. Now we'll be talking about energy more, but I just wanted to immediately point out that energy and work are so closely related. Energy's capacity to do work has the same units. Now the next point has to be made, and I like to demonstrate it this way. So this table here is 1, 2, just under 2.5 meters. And I can now lift this ball and carry it across the table horizontally and then drop it down there. And one might think I just did 70 newtons times 2.5 meters of work. Not the case. Okay. So there's a technicality in this definition. So if I just lift this thing, a centimeter and carry it across, I'm straining. This is hard work, right? But no work has been done in the physical sense because the displacement and the force have to be parallel. So that's an important point here. So we're adding to this discussion for work to be done F and delta X must be parallel. You'll notice I'm writing them as vectors now, because they are. And there's actually a technical way to express that. I'll just call this the scalar product. It's not something we need for this course, but scalar product is also called the dot product. You guys may have seen this, may not have seen it. But we can then define work equals vector x scalar product delta x. Okay. And the definition of the scalar product is F dot delta x. This just generalizes to vectors, is equal to the magnitude of x times the magnitude of delta x, I'll put little dots there, times the cosine of the angle between f and delta x. And the point is that if these quantities are perpendicular, there's no force at all. Because cosine of 90 degrees is 0. So if, we'll call this angle theta, if theta equals 90 degrees, then cosine of theta equals 0, then the work equals 0. And this is precisely the example I showed you with the bowling ball. So once you're aware of that, you know that your displacements and force are parallel, and then the example of lifting something is the perfect example to remember. Just lifting things. So this is a more technical definition, but the one you remember is the one I have up there. Good, so once we have this definition of work and this example, now I didn't write it down, maybe I should. Oh, actually, there's a good demonstration of this, of the point I was about to make in terms of doing the work. Sure, I'm straining to lift this thing at arm's length across the table, okay? But if I were smart, I would have just rolled it across as effortless, okay? So you'd agree there's no work done, okay? I just effortlessly rolled this thing across the table, and I've accomplished my displacement, but it was perpendicular. The displacement here along the table is perpendicular to the gravitational force, the weight. Okay, I'm going to retire the bowling ball. It's done its duty. I'll just keep drawing the bowling ball. Okay, so next once we have this definition, and again, just lifting things to appropriate quantities. My next example is the ramp, or my next example, not the ramp, the staircase. I'm going to make some very low stairs. And I want to take the ball up this height h here. Here's A. I'm going to call this point B and this point C. So I can do a couple of different things with the ball. I can, here we'll draw it red. If I start right here, I can lift it up and then roll it forward, lift it up and then roll it forward, and eventually I end up here. So that path, I did these little increments of work, and then no work on the horizontal. The total work ended up being just the weight times the height there. So let's call this thing mass M. And then work from A to C is the weight times the height. I could also do the work from A to B to C, which would be to roll this ball along here and then lift it all at once. Same amount, right? mg times h. The third thing I could do, since I have colors, I'll put it all on one picture. I could have a smooth ramp all the way to the top. So the blue line is a smooth ramp, not a stepped ramp. And would it be the same amount of work? That's the question. So let's call it blue work here. AC, let's say for the smooth ramp, equals what? Well, here's what we could do. We could put the ball here, do our free body diagram as we've been doing, and then we would know that the downhill force, would have been mg sine alpha in magnitude, because we've done that before. And the length of the blue line, I'm just going to call L. Okay. So this downhill force here, mg sine alpha, is our alpha. Yeah, make this picture big if you want to have everything, otherwise do two pictures. Not a bad idea to put it all in one. And is that equal to these two works up there? But we have sine of alpha is simply equal to h divided by L. So what do you know? mg h divided by L times L. L's cancel, we get the same thing. So the important point here is you can get from A to C from the bottom to the top here by different methods, and it's always the same amount of work. And for this example, let's stress that there's no friction. We're going to pretty much take friction out of the discussion of work because I'm trying to get to the basic concepts the fastest way possible, the simplest way possible. So these examples show that same amount of work, if there's in the frictionless world, so to speak, it takes the same amount of work to get from the bottom to the top, regardless of what path you take. So that's important note here. Same amount of work. Okay. now we have work, we have some examples, we have an energy, the capacity to do work. Okay, what's next here? I'm going to introduce something called potential energy. We can use the abbreviation PE for potential energy. And we'll also use the letter capital U. But for starters, potential energy here, I'm going to think of it as stored work. And I can refer to my picture again. If I rolled this thing up to the top of the ramp and just leave it there on level ground, I can actually claim to have stored that work. Okay. So my example is again rolling something up the ramp and leaving it on a shelf here. Okay. Started at the bottom, took it to the top. It's up there. Now, if it's stored work, why would I want to store it? And the answer is because I can get this stored work to do some work for me. Okay. I put the work in, stored it up there, and now I can get the work back again. It's like putting money in the bank in a number of ways. This could be the weight on a grandfather clock. Example, the weight of a grandfather clock. I think that's what they're still called. You know, look this up online and maybe get a picture of this for your notes. It'll be interesting. So a grandfather clock, some big object here, there's the hands. So what makes this thing run is that there's a mass that's been wound up here. There's a mess of gears I'm not going to explain, but this mass drops down over the course of an entire week, and via the gears and pulleys it actually turns the hands of the clock. So it actually is doing work for an entire week, and what's keeping time at the same time is a pendulum swinging back and forth with little ratchets hooked up to the gears. So if you're interested in how a grandfather clock functions, look that up. What drives it is the weight that was lifted from the bottom to the top at the beginning of the week, and then it gradually goes down all week. So that's clearly been stored. Okay, it's been stored work, and we say that there is potential energy in this system right here. So potential energy is stored work, and I'll write gravitational potential energy we're going to use the letter U, capital U, subgravity potential energy. So let's go ahead and make sure we have this in our note. Potential energy or capital U. So I'm going to use U sub G is just equal to M times G times Y, where the positive Y-axis points up. So yeah, this is the all-time great example, actually. We're going to keep using this because you wound up the clock, lifted the weight, maybe a meter, meter and a half at most, and then it goes down and drives the gears and everything for an entire week. So there's your stored work, and potential energy is stored work, and this very important example is the gravitational potential energy. Okay, so far so good. Let's see how we're doing time-wise. Great. Yeah, this example up here was important, so make sure you have some good information on that. there's more than one way for that work to be done. We've lifted the mass up. With the grandfather clock, it slowly ticks on down over the course of a week. That's one method of using the work for our own purposes. The other method I'll now describe. So let's call this work done by a moving object. And we're going to take the same example. So we rolled our bowling ball up to the top of the ledge here. You know that's the height h. There's the ball. How else can it do work? Okay, the way it can do work is if, suppose we have a nail or a spike down there, we want to drive it into the ground. Okay, so we've tipped the ball off, and it falls down here and drives the spike into the ground. So we can say the falling mass drives a spike into the ground, or a nail into a board, something like that. Drives a spike into the ground. And then here's the thing. The work done is the force times the displacement. So the work done is that mgh. So work is equal to mgh. That was our stored work. But now we used it to drive a spike into the ground, is equal to the force times the delta x of driving the spike into the ground. And you can see if the spike is short, then that force is enormous. And for example, with a bowling ball, you wouldn't want it to land on your foot, right? But if it lands on a spike, you could drive it into the ground. So here's my point. Falling mass drives a spike into the ground. What was going on the very instant before it hit the nail? It was moving with a certain speed, okay? And what we say is the work up here was converted to energy of motion. The work was converted to energy of motion, converted to energy of motion. We'll put quotes around here because I'm about to give a definition. Energy of motion, and that's called kinetic energy. So work is converted to kinetic energy. Let me use this section of the board right here. Work, parentheses, mgh, is converted to kinetic energy. Kinetic energy, that's what this energy of motion is. And kinetic energy, or capital K, will have K is equal to 1/2 mv squared. So this is a very important definition. 1/2 mv squared. And let me show you how that comes into being. Because this definition is going to arrive straight out of the law of free fall. I could have done it in that order. And we're going to have to come back to this gravitational potential energy now. So we're still referring to that picture up there. So I'll just do a small version of it. H, okay. The ball's going to fall down here. we have from kinematics, we have v squared equals v0 squared minus 2g x minus x0. Okay. Just our kinematic formula, we're going to release it from rest, okay? And then the x minus x0 is going to be minus h because we're going from higher to lower, okay? And then we're going to get v squared is equal to 2gh. And what does that tell us? That tells us, in fact, now you want to leave a little space everywhere, so that tells us v squared over 2 is equal to gh. So this is purely kinematic law of free fall. All I have to do is multiply both sides by m, and here I have the potential energy or the work, and here I have the kinetic energy. So if something falls through a distance h, it acquires this much kinetic energy. Okay, so yeah, this is the condenser right here of where we got that definition from. We took it right out of the law of free fall and kinematics. Simply by multiplying by m, so let's go ahead and write, multiply both sides by m. By m, okay. And then we get this, and what we had is potential energy was converted into kinetic energy, okay, what the equal sign is. So potential energy converted to kinetic energy. Okay, so now we have all the ingredients together for us to talk about energy. There are basically these two forms of energy at this stage of the semester. There is kinetic energy and there is potential energy. It's one, the other, or both. And so I'm actually jumping ahead towards the end of the chapter because we want to get this point early on and then fill in some details. So go ahead and read the chapter. This is chapter 5, but you'll see that I'm working our way through to the end to skip over a lot of details to get the important point across that, we have potential energy, kinetic energy, and what's going to come next is conservation of energy. And I'm going to give a bunch of examples of that, and then we'll work through with more technical examples. So far we have work, right? And then we have the concept of energy, then we have the concept of potential energy, and now we have the concept of kinetic energy. So everything is in place. Each of these I have a good example for. Right? Lifting something, the capacity to lift something, storing something that you lifted, and dropping it and having it, move around. So I'll even put potential energy of gravity as mgy, kinetic energy is a half mv squared. Work is force times displacement. Okay. So there's our conceptual framework now. And I'm going to roughly state the idea of conservation of energy. Conservation of energy. And that is in the absence of friction. Just keep friction out of the mix. Everything has to be an ideal system, no friction. In the absence of friction, the total mechanical energy of a mechanical system is conserved. So, absent friction, kinetic energy plus potential energy is conserved. And conserved means equals constant. Now I want to show you the systems for which this is applicable. Okay, so first of all, there's no friction. And next we're going to talk about the pendulum. Now in a normal class, we take that bowling ball and hang it from the ceiling and we have a really nice demonstration object. Okay, I'm not going to have that for you. But nonetheless, let's discuss the pendulum. And you draw a pretty large pendulum so that it swings in an arc. In fact, I'm going to use more board for that. So yeah, let's draw a large pendulum. We have some room to label things, okay? If it's just hanging down here, it's got a length L and a mass M, and then it can swing up in semicircular arc here, okay? So suppose we release it from rest here. Release from rest. Okay, that's a pretty aggressive pendulum. We release it from rest and it's going to pick up speed. Down here it's going to be moving the fastest and then it's going to slow down, and in the ideal case it will reach its original height. If you build a pendulum and do this, string and a mass on the end, you'll see that it will come close, but it will never reach it exactly. And the reason for that is friction. So the ideal pendulum reaches its original height. So I can actually identify these. Suppose I released it from rest here, then it'll swing through and reach this height right there. So that's something you discover empirically. What does that have to do with energy? Let's go ahead and draw a y-axis here. There's a y-axis. And we're going to take this one right here as being the initial position. So if this is 0, okay, yeah, make a nice sized graph here. If this is your origin on the y-axis, then we're up here at L, okay? So the potential, and here's what we'll do. We will label points A, B, C, D, E, F, G. Now we can talk about all these points here. So here we go. At A, we have potential energy is equal to mgl. Okay. At D, we have potential energy equals 0, but kinetic energy equals 1/2 mv squared. And these two are equal. At any place in between, we have a combination of potential energy and kinetic energy. So, any place in between, and I've labeled a few of them, B, C, E, and F. We have kinetic energy plus potential energy equals constant, and right underneath here, I'm going to fill in going to fill in the relevant equation. So what do we mean by this? Any place in between, we have 1/2 mv squared, I'll write or, plus mgy equals this constant. But because we started out at the top, that constant was the work at the top, which was just mgl. So this is an example of setting up the energy equation. It's a really powerful statement. Now, I skipped a number of things, namely the direction of the force, okay? The direction of the force was always down, and the displacement was not perpendicular to the force, okay? It was not parallel nor perpendicular. So we already proved, though, that it didn't matter how we got from one place to another. If there's no friction, it's always the same amount of work, okay? So that work is converted to the kinetic energy, and this is the general expression. And you're going to learn to set these kind of equations up, and they give you a really quick answer. So this is the example, once again, for releasing the pendulum from rest at point A. That's exactly what I'm talking about here. And I can get the speed at any position, right? You give me a position, I'll give you the speed, and you give the speed, and you can get the position, or actually two positions. So for a frictionless system, you want to be able to set up the energy conservation equation. Another way to write it is so we can also write, let's see here, for any of these two places up there, I'll just write energy at A is equal to energy at any one of these others, B, C, D, etc. Should I choose? I'll choose E. Actually, I'll choose B, because I want to keep this general. Energy at one point is equal to energy at another. Then what you do is you write kinetic at A plus potential at A equals kinetic at B plus potential at B. And this is one of these recipes. I encourage you to write out all the steps, especially at first, because then nothing can go wrong. You got a frictionless scenario, you write energy at A is equal to energy at B. That's what conservation means. Then you've got the kinetic, and then you can write 1/2 mv sub A squared plus mgy sub A is equal to 1/2 mv sub B squared plus mgy sub B. And then you've set up a true equation that allows you to solve for one unknown. So this is all the same, these are all versions of this. They're all equivalent to each other. Okay, so yeah, that's an important way to go about things. Let's see how far we've gotten. Good, yeah, I'm gonna assign some homework problems now. And this really contains a lot of what we're doing. We made it all the way close to the end of the chapter because I wanted to teach you the law of conservation of energy. That's what we're looking at right here. So I'll label this again, conservation of energy. Because once you see this, it's really this simple. And I'll give you example systems And the reason I go to the end of the chapter on this section is because experience shows that spending too much time on the details, by the time people get here, they no longer get it, okay? But this is really basic. You've got your frictionless system, you just take 2 points, there's no friction, and you can write out your energy equations, and you get this true statement here that you can evaluate. Okay, good, we'll work on this. Next time I'm going to have to give a lot of examples, because I think I want to, I don't want to run over right now. So this is homework for lecture number 14, and we are now in chapter 5. I'm going to give a couple of basic work homeworks. Concept of work, I better consult text here. This is a great chapter, so okay. Always doing the problems. Okay, so we'll do chapter 5, problem 1. Now, of problem 4, I just want us to do actually, let's just say 1 and 3 for starters. Forget 4. So 1 and 3, these are very basic. And 7a. Actually, 7a and b. 7 includes friction. So these are just work problems including friction. But now some energy problems without friction should be good as well. So energy problems without friction. Ah yes, 25 is a good one. It's a projectile type of problem, so we can never get too many of those. Okay, you can use energy in projectile motion once you know about it. So, very useful problem. And yeah, and 33 is very basic. But yeah, let's do those. Next time I'm going to do a bunch of examples explicitly, possibly some of these as well, other ones as well. Okay, good. Enjoy. See you next time.